In this video, we're going to talk about finding extrema on an interval. So I've got some grammatical issues here at the beginning. By an extremum, we mean either a maximum or a minimum. Now, I'm going to define those exactly in just a moment. But a maximum, you can probably guess, is sort of the largest value of a function, and a minimum is the smallest value of a function, or at least they have something to do with that. So maximum and minimum are singular forms, as is extremum. Extremum is an all-encompassing term. An extremum could be either a maximum or a minimum. And then the plural forms are maxima, minima, and extrema. Alright, so here are the definitions that we're going to be working with. Suppose you've got a function f that's defined on some open interval I containing the number c. If f of c is greater than or equal to f of x for all x in the interval I, then f of c is the maximum value for f on I. So what we're saying is that f of c, the y-coordinate at x equals c, is greater than or equal to all the other y values for values of x in the interval. And if f of c is less than or equal to all the f of x's, then f of c is the minimum value for f. And then the minimum and maximum values are each called extreme values or extrema for f on the interval I. The extrema on an interval are also sometimes called absolute extrema or global extrema for the interval. And the extreme value theorem is useful. It says if the function f is continuous on the closed interval from a to b, then f has both a maximum and a minimum on that interval. So why does the theorem require the function to be continuous? Well, can you think of a way that you could have a discontinuous function that maybe does not have a maximum or does not have a minimum or doesn't have either one? Well, how about the function f of x equals 1 over x on the closed interval from -1 to 1? That graph would look not like that. That graph would look something kind of like that. There is no maximum because the graph keeps going forever, both up and down, so there's no minimum either. So why does the theorem require the interval to be closed in order to guarantee that there is a maximum or minimum? Well, okay, let's take a look at a very simple function. Let's just look at f of x equals x on the, not a closed interval, but an open interval. F of x equals x on the open interval from 1 to 2. So you know what that means. It means we're not including the endpoints. So the graph would look something kind of like that. There is no maximum value because that point isn't there, and there is no minimum value because that point isn't there. Alright, so now we're going to talk about relative extrema. If there is an open interval containing c on which f of c is a maximum, then f of c is a relative maximum or local maximum, as opposed to a global or absolute maximum that we talked before. We also say that f has a relative maximum at c f of c. And if there is an open interval containing c on which f of c is a minimum, then f of c is a relative or local minimum for f, and we say that f has a relative minimum at c and f of c. So let me give you an example. let's say you've got a function that looks sort of like this. There is no absolute maximum, there is no absolute minimum. But there is something called a local maximum and there's a local minimum. You have a local maximum right here because if you're to say look at that interval, the function attains a maximum on that interval at that point. So this is a local maximum, and there's also a local minimum. This is a local minimum. If you limit yourselves to just this interval, then the function does have a minimum at that point. Now we're going to look at where extrema occur. If we're talking about a closed interval, you could have a function that looked something kind of like this. So the graph of the function, it consists of just the part that I've drawn here. And so the absolute minimum occurs at A, and the absolute maximum occurs at B. But if I had drawn this hill so it was very tall and extended past this y value, then I could have had the maximum at this hilltop. Similarly, if I had pulled this valley down lower, maybe I could have had the minimum there. Alright, so these points are very important in the discussion of extrema. And let me draw another picture. The function could have looked, instead of the local maximum and the local minimum being at the tops of these nice smooth hills, we could have had something like this. So the local maximum could have occurred at a cusp, the same with the local minimum. Now these are actually not only local maxima and minima, or local maximum, they're not only local extrema, they're also absolute extrema since they're the highest and lowest points on the graph. So these kind of points are important enough that we give a name to them. These are called critical points, or the x values are called critical numbers. Here you've got a horizontal tangent line, and so the derivative is 0. And here you have cusps, and so the derivative is not defined. So this leads us to the definition of a critical number. Let the function f be defined at c. So the function has to be defined at c. If either the derivative at c is 0 or the derivative is undefined, then c is called a critical number of f. And if f has a relative extremum at c, then c is a critical number. The only place to look for relative extrema, relative maxima, relative minima, is at critical points or critical numbers. Either places where the derivative is 0 or places where the derivative is undefined. Alright, so can we find the critical numbers for f of x equals x squared plus 3x? Well, what we need to do is find the derivative, and that's going to be 2x plus 3, and we have to ask ourselves, is this derivative ever undefined? No, it's defined everywhere. In fact, it's continuous everywhere. It's a line. This graph of this function is a line, and so the function is very well behaved. It's continuous everywhere. It's even differentiable everywhere. There are no places where this is undefined. Well, are there any places where 2x plus 3 equals 0? There certainly are. Well, or there certainly is. There is one. x equals negative 3 halves. That's the only critical number. Let's try another example of finding critical numbers. Here we've got the function f of x equals the cube root of x plus 1. That can be rewritten as x plus 1 to the 1/3 power. Alright, so f prime of x is equal to 1/3 times x plus 1 to the minus 2/3 times the derivative of the inside function, which is 1. Let's rewrite it. We've got 1 over 3 times the 2/3 power of x plus 1, which is also equal to 1 over 3 times the cube root of x plus 1 squared. Alright, so this function is a fraction. It's never going to be 0 because the numerator is never 0. But is the denominator ever 0? In other words, is the derivative ever undefined? Well, if the x plus 1 is 0, then the function is undefined, and so that would mean that x equals negative 1 is the only critical number. I use the abbreviation CN for critical number because I was running out of paper.